Hi, I'd like to check if I'd like to evaluate if two features that I found in along the semi-major axis become clearer when adjusting the semi-major axis by dividing the semi-major axis by the square root of the stellar mass, or is there another optimal adjustment by the stellar mass? And the two features are the peak gap peak feature and the eccentricity correlations. So first like to check if the inner peak gap and outer peak, if the boundaries between these two features become clearer. And then second, is the running mean of the eccentricity found a correlation, well, different correlations with semi-major axis. Do these become more clear by adjusting the semi-major axis by dividing by something like the square root of the stellar mass? So what I'm proposing for looking at the peak gap peak feature is to see if the gap size becomes larger uh, when you divide by the stellar mass by the square root, or something close to the square root of the stellar mass. But have to measure that. Of course, the gap size changes in absolute terms when you're changing when you're changing your the power of the stellar mass that you adjust with. So we need to divide it by the width of the broad peak, but the broad peak is poorly defined. Uh, Now, by dividing by the width of the broad peak, that'll cancel out uh, the stretching or the squeezing by adjusting by the stellar mass. But we need to try to find a way of measuring the width of that broad peak, since it's so diffuse, and probably particularly pay attention to using similar objects to define that width. Then second, want to look whether the eccentricity correlations with metallicity, do they get clearer with adjusting the semi-major axis by what power of stellar mass. So, and I'll just briefly say that the eccentricity correlations, they're basically the closer into the star, or originally found at short periods less than 100 days. And this is something that Dawson and Murray Clay found at around the same time I did, that at these short periods, the eccentricity is quite a bit higher for objects, and by objects I mean planet star systems. I mean all the parameters for objects that have the stellar mass as solar or larger than solar, that compared to the eccentricity, to the mean eccentricity for objects of with the star that has lower metallicity, the eccentricity is higher with higher metallicity. And then as you get up in higher, as you increase your semi-major axis or increase your period, then you run into a period where the correlation appears to disappear. Perhaps there's even a small region where the running mean of the eccentricity is higher for the low metallicity objects. But then in that region, we're actually running into where the gap is. And so we actually have few high stellar mass objects to compare with. Once we're well within the outer peak, then it appears that this correlation returns. That is, that there's higher eccentricity for objects with the same or higher stellar mass. Now, as I'm doing this, want to also check, does the eccentricity actually correlate more with the mean distance between, well, with the density basically, or so the density would be basically a running mean of the distance between neighbors in semi-major axis. And so I'll also ask, is this more clear using an adjusted semi-major axis adjusted by the stellar mass? Uh, so I have these two projects, uh, and then so these two projects I have the next slides where discussing in graphics using slides I've shown previously in graphics what I'm seeking to find out. Several of the other students used AI, and I don't have any experience using AI. I'd be very interested in if AI could go look for these sort of things. So anyway, this is the plot of the mass of the star versus semi-major axis, and I've explained that you can see that here's the gap, and the gap does seem to have a boundary that's slanted by stellar mass. And so that's what got me onto dividing by this. This is roughly the square root. This slope is roughly the square root of the stellar mass, but it might be just the stellar mass to the 0.45. Actually seems to fit slightly better. So this is the zoomed in. This is coming out a little bit. You'll notice that that the gap doesn't extend below around 0.8 stellar masses. So here we're looking at the gap here for the adjusted semi-major axis, and see that it's wider than what I had previously shown and previously published, the gap in period, which is a different power of stellar mass. And of course, I have to compare it to compare apples to apples. I have to compare it to the width of the broad peak. So these two plots, the red plot here is just objects of the population that I found the gap in. The metal-rich objects with single stars and convective stars that are convective. So neither too high or too low of mass in stars. And so that's what the red plot is. And then here I only show the equivalent of the red histogram. Thank you.